So today we're going to be looking at length contraction, which is another consequence of Einstein's theory of special relativity. So let's imagine that we've got a spaceship that's travelling at half the speed of light and a person that's looking at it. Okay? So after 1 second, everyone can agree that the spaceship should be here. It's travelled 1.5 times 10 to the 8 metres in 1 second. Yeah, because it's travelling at half the speed of light. But we know from my previous video on time dilation that actually the 1 second that the person measures going from here to here isn't going to be the same as the second that the spaceship measures from there to there. The spaceship is going to experience time as being shorter. So when the person measures 1 second, the spaceship is actually going to measure about 0.83 seconds. But it's still moved from there to there. And it's still travelling at 0.5 c. The speed hasn't changed. So therefore, if the speed hasn't changed, but the time is smaller, the distance must also be smaller. And this is my idea of length contraction. That when we're travelling at or close to the speed of light, lengths appear to be smaller in the direction of travel. So this length would appear to be smaller, but all those other lengths would appear to be the same. The length contraction only happens in the same direction as the travel. So our equation is over here. This is the observer length, and this L0 is the proper length. So that is the length of the object when it is at rest in a frame of reference, okay? And then we've got 1 minus v squared over c squared again, where v is the speed of the object and c is the speed of light. So let's have a look at this train. So I've got a train that's moving at 0.9 of the speed of light. Now, the person on the train has measured it and says it's 12 metres. Woohoo! However, the observer does not measure it as being 12 metres as well. So what we need to do is we need to work out how long the observer thinks this train looks. So we're going to use the equation here. L is equal to L0 square root of 1 minus v squared over c squared. Now, the proper length is the length when this object is in rest in its frame of reference. So the object's frame of reference is going to be when it's moving, so it's the length that we measure inside the train. So that's going to be our 12 metres. And we're going to multiply it by 1 minus v squared over c squared. So if I just grab my calculator, I'm going to do 12 multiplied by the square root of 1 minus v squared over c squared, would just be the same as saying 0.9 squared. So I'll wind up with c squared on the top, c squared on the bottom. I can just cancel them. And I get an answer of 5.23 metres. So you're going to say the same thing you said last time. Hannah, the maths is great, but what's the evidence for this? And I'm going to show you the evidence for this. And we have to go back to our lovely, friendly cosmic muons. I'll see you there in a second. Okay, so we're back to my friendly cosmic muons. So cosmic muons, remember, come from outer space. They've got a really small half-life, about 1.5 microseconds. We detect a bunch of detector 1 and then detector 2, 2 kilometres away. We predict that most of them should have decayed. How much are most of them? Let's find out. So time is equal to distance over speed. So that's 2,000 metres or 2 kilometres divided by the speed of muons, 0.99 times 3 times 10 to the 8. So the time it takes for the muons to get between the detectors is 6.7 times 10 to the minus 6, or 6.7 microseconds. So let's work out how many half-lives that is. So 6.7 divided by 1.5 would give me 4.5 half-lives. So if I started off with 100 muons, or 100%, after 4.5 half-lives, I would expect to have 4.4% of them remaining, okay? However, that's not what we saw, and it's all to do with this idea of length contraction. Because to the muons, the length they travelled wasn't 2 kilometres. They're travelling nearly at the speed of light. That length to them appeared to be shorter. So we're going to do L naught square root of 1 minus V squared over C squared. Now, the proper length is where this length is going to be at rest. So that is with respect to the Earth. So the proper length is going to be 2,000 metres, because on Earth, this is stationary. Okay, this distance between the detectors, it's stationary. It's measured by a stationary object. So that's going to be 2,000. I'm going to multiply it by the square root of 1 minus 0.99 squared C squared over C squared. So I can cancel out my C squareds. So I get an answer of 2,000 multiplied by 1 minus 0.99 squared. I get 282 metres. So I'm going to work out what the time experienced in between the detectors is this time. So time is equal to 282 divided by 0.99 times 3 times 10 to the 8, which gives me an answer of 9.49 times 10 to the minus 7 seconds, or 0.9 microseconds. So actually, that is now less than a half-life. So now I can estimate that more than 50% of the muons that were at detector 1 should be at detector 2. Estimate's no good, let's work out how much. So we're going to do 0.9 divided by 1.5 to find out the number of half-lives, which gives me an answer of 0.6 half-lives. So 100 multiplied by half to the 0.6 would give me an answer of 66%, which if you've watched my video on time dilation, we get the same results if we use those equations as well. So there you go. That is the evidence that special relativity was correct, and very fast moving particles experience lengths to be shorter than they are. So I hope you enjoyed this video, and don't forget, if you want the notes on this topic, to check out my resources on the MyEdSpace website. And if you want more content like this, don't forget to drop us a subscription to this channel. I'll see you soon. Take care.